All right, who cares about dirt?
I do.
Good.
I care about dirt.
Zoe, do you care about dirt?
Alright, dirt's important. Without dirt, we wouldn't be
You guys don't
here.
care about dirt? Forget dirt? We're always trying to get rid of dirt, right?
Dirt.
Don't pay attention.
Dirt is great.
Dirt is great. Thank you, Justin.
Dirt's
You're
important.
absolutely right.
That's where plants.
Soil is crucial, okay? The two main things that soil provides structure-wise is water and air, as you can see right here. Water and air, okay? When plants get water, let me clarify this a little bit. Plants that are smaller plants and grasses, basically, bless you, plants that are not trees, terrestrial plants that are not trees, or larger bushes and stuff, they get most of their water from the moisture of the soil. Soil, of course, can get moist. It can hold water in there. Its ability to hold that soil moisture, that water in there, is based upon a lot upon its structure and also how much organic material is in it. Okay, but that's the source of water for a lot of different plants. They absorb it right there from the soil, and it's important that soil be able to hold on to it. Now, trees do put down. They get water from the soil moisture as well, but they also put down a taproot down deep, and that goes into the shallow aquifer. And that's one reason why trees can continue to sustain and grow year after year after year, whereas a lot of other plants, they're annual plants because they simply dry out during part of the year and they die off and then they come back in the next generation. Not only does the water, of course, is crucial to plants, they need for photosynthesis, but a lot of people don't realize is that plants need air as well. As a matter of fact, a lot of people end up inadvertently killing their plants because they water them too much, or the soil that they have their plants in does not drain well enough, and that soil stays wet rather than moist. And basically, the plants, which usually breathe through their roots, they end up drowning, literally. And that they can't get oxygen. They need oxygen to carry out photosynthesis, and without that, they cannot grow. As a matter of fact, when you use hydroponics, if any of you do hydroponics, which I'm sure you would do for purely legitimate reasons, one of the things that has to be done with the water supply that those roots are in has to be aerated. It'll either be circulated, so it'll fall like a waterfall kind of thing, or you'll have a bubbler in there that aerates that water because the roots will then absorb the water, the oxygen that's dissolved in the water. But if you don't, those plants will die and like I said, drown in a sense. So they need the soil for that. They also, of course, need that soil for their minerals. Okay, and that's going to come really from two different sources. All right, part of it will be from what we call the native parent material. Yep, parent material. There we go. Okay, so this is just bits of rock and stuff. This ties in with what we just learned about with the rock cycle and how mountains and things are formed, and then they are eroded away by wind and water. The little bits of rock then are washed down into and settle down into the lower parts of the land, and from there they mix with organic material and become that soil altogether. But the little bits of rock and stuff are known as your parent material. So soil is, you can make a little side note here. Soil is made out of soil. Want your ingredients for soil? You have your parent material, 1 part parent material, and then however many parts of the organic material, which is known as humus. Humus, not to be confused with hummus. You don't want to go to a party and bring a big dish of humus along with you. It may not be that, unless you go to a party with some worms, they would appreciate that, but otherwise, not so much. So that's what it is. You've got your bits of rock and sand and stuff like that. And then you've got your decaying organic material. That's your humus in there. Those two together provide for the plants. Now, as I said, not only does soil supply the physical structure so those plants can get water and air, but it also provides the minerals for those plants. And that really comes in two different ways. One is from the minerals that are in that rock, bless you, in that parent material, slowly dissolving away, adding phosphorus and calcium and iron and all those kind of good things that are in the rock. The plant's able to absorb those to a certain extent. And then you have the internal cycling that comes from decomposition. So this is the internal cycling. This happens when things defecate and die, right? And if you remember, I talked at the beginning of the year, I talked about how it would actually be better for us if we would go outside to the orange groves and relieve ourselves, and then take grandma to the wheat field and drop her off there when she died, that kind of thing, because technically, because that's what happens in nature, of course, when things do their business, or when things die, they fall down, or they do it into the soil, and it goes in there, and then those materials can be broken down by decomposers, bacteria and funguses, and the plants can then absorb those minerals right back into their systems, and therefore you have a type of internal recycling. So plants really need both of those. They need to have that decomposition, internal recycling part going on that I just talked about there. And then they also need, from the little bits of parent material, the slow dissolving of nutrients that occurs there. And that's also, like I said, before the break, that's how the rock cycle was important for us. It gives us a continuous supply of this, the inorganic part of the soil. Okay. Now, when it comes to this parent material, it's going to have different properties based upon, of course, its chemical composition, which we really can't cover the many different types of mineral components that can be in there. They can also be broken apart simply by size, broken down simply by size. And the designations they use for that, there are some that you're probably familiar with. Gravel is going to be your largest. Sometimes some soil scientists, believe it or not, there is such a thing. They don't count gravel as part of the soil. Rocks is not what we have next. Sand is. It's a little bit smaller than gravel, as you can imagine if you think about it. And then silt is just kind of a very fine sand. And then clay, it's got the finest particle size of all.
Wait, so it's silt?
Silt.
Sand.
Isn't clay like
Gravel, sand, silt, and clay.
Clay is like hard.
But silt.
It is, but if you ever look at dry clay and like
Is silt
the
sand?
dust and everything it puts over, the actual particles, the dry particles of clay are extremely small.
No.
So, and that affects it.
Okay.
So as you might imagine, the size of these particles has a lot to do with their soil, with their water, and air holding capacity. Right, Jody? Right. So, and the relationship is that the smaller particles, the finer particles, are going to hold more water and less air. So try to remember this right here, okay?
You were right, man. You were right.
So I forget. I think it's the converse. I can never remember those logical terms and everything. But the opposite is true.
Conversely, yeah.
So let's say sand. I should probably eliminate gravel. Let's say sand. Is sand going to hold a lot of water or not much water? Less or more? Sand. Less. Sand's going to hold less than clay. What about air? Sand going to hold more air or less air? More air. Sand will have more air pockets, more air spaces in it. The particles bigger. They'll tend to have those air pockets in there more so. And then it changes as you go along. So clay is going to hold the most water. As a matter of fact, clay can bind together, of course, and just stop water altogether from soaking down in. That's why we have clay aquaclude in Florida. But very little air, and then vice versa, of course, with more water, less air when it comes to clay. Okay, so everybody comfortable with that spectrum of water and air and how they're opposite and how they're affected by the size of the particle. Okay? All right, so if you go on Soil Book, you can check out your favorite soils profile. And this basically means what it looks like from top to bottom. Remember when we went outside and dug a hole? Remember that?
Yeah.
Good times, huh? Love. I dug that. Did y'all dig it? I dug it. Yeah. So anyway, what we were looking for was the soil profile. the different layers of soil. And part of that is something called the overlay, or each one of these is, each one of the layers is a horizon. You know, horizons are like that, unless you're lying on your side. And therefore you got your O-horizon, that's primarily leaf litter. So the kind of division here is that this stuff has really not decomposed that much yet. Much more of a factor in certain ecosystems such as deciduous forests. Like up in the up in the Appalachians right now, if you were to walk through the woods, you'd be walking through deep piles of leaves and stuff because the trees have shed their leaves and everything, and that's going to be on there, and eventually that's going to decompose and go into the soil and become part of the A horizon, which is your topsoil. Okay, so this is usually the one that looks more black in color, and this is where you're going to still have organic material. This is where this is where your decomposition is taking place. You will find in the topsoil, this is where you're going to actually find living things. Bugs and worms and stuff as well are going to be in here. This is also where you still have air in the soil, so this is sometimes called the zone of aeration. So go ahead and write that down, zone of aeration. The A horizon. Okay? And so with a lot of your shallow plants, this is where their roots exist as well. Your smaller plants, I mean. And then you've got your B horizon, which is underneath that. When you get down to here, it's at least in Florida, it's more of a sandy type to it. If you were in Georgia, you'd hit the clay and everything there. It has a distinctive color to it oftentimes, based on the minerals that are in it. This is where I'll take water. This is where your precipitation soaks down into, and this is also where you find your shallow aquifer. Oops. You get the idea, right? Precipitation. So you have a lot of mineral content in there because the water soaks down through there and takes it with it. Underneath that, I didn't list it here, but you have bedrock. Sometimes it's called the C horizon. You'll see on the diagram we have what they call it the C one. It's bedrock, though. It's solid rock material. It's generally not considered to be part of the soil. But the water's not going to soak down as much into there as well. So this is, like I said, this is where you typically have your shallow aquifer, and the minerals that are in the soil and everything can soak down to that level. Those that get washed out. Okay, soil horizons vary from place to place. One of the big factors that affect soil horizons are plants. For example, grasses, as you probably know, have got a very dense, interconnected network of roots and rhizomes and all kinds of stuff, botanical things there I don't know the name of, but they form a very dense mat. And they also tend to die back in the dry season. So that area will die, and then another layer of grasses will grow on top of it, and therefore they can build very deep topsoils. So in the grassland areas, you find very deep topsoils, and some of them as much as 2 or 3 meters deep, as far as how thick that topsoil can be. Where if you remember when we dug out here, it was a few inches deep. Florida does not have a significant topsoil in most places. Well, we have grassland areas. I take that back. In our forested places, like the pine type forests that were native to this place before we built in this area, not usually a very deep horizon there. And then climate has a lot to do with it as well. Like in the rainforest, because there's so much rain, it tends to wash out the topsoil a lot. There's a lot of decomposition takes place there. They have a very substantial B horizon in the rainforest. Any questions? Alrighty. Okay, so how can we reduce this soil erosion and depletion? So there's two main ways in which soil is made useless, rendered useless, or is actually moved away. That moving away part, that's called erosion, and that is something that happens through wind and water. Okay. The thing about it is that plants and soil have this kind of mutualistic relationship with each other, in that the plants, of course, need the soil, but then the soil needs the plants. The physical structure of the plants, the roots and everything holds that soil in place. And also, in the case of trees, they will form a wind barrier, so that can also reduce the amount of soil that is eroded away through wind and water. So as long as those things are still in place, then in natural settings, soil erosion is generally not much of a problem. That is, of course, unless we do things like deforestation and changing that landscape and doing all the other kind of things like people do to do that. So we understand how to reduce those things and not do those so much. So we're going to focus on soil conservation primarily from a farming perspective. And that's because a lot of what happens to soil is due to poor farming techniques, and another source of problems is acid deposition. Now in the first part here, this is a physical loss of the soil. The soil is blown or washed away, it's gone, okay? In the second part, when it comes to poor farming techniques and acid deposition, that's when the soil becomes demineralized, loses its nutrients, but then if it loses its nutrients, then the plants are going to die, and therefore once the plants die, they're no longer holding the soil in place, and you have erosion, you have the physical erosion as well. So one tends to lead to the other. So we'll look at water erosion first. To reduce the amount of erosion that happens from water, we want to reduce the amount of water that we're using. So we want to use low volume irrigation. With a drip and mist system. Now drip and mist system works well in that one of the problems, of course, you have with low volume is that when you have that low volume, you have increased pressure. It's a physical principle. We talked about that when we talked about water conservation. Well, you don't want high pressure blasting the roots of your plants and washing the soil away that way. So drip systems have just basically a small opening for the water to come out, so there's not much of it comes out, but then it hits a little overhanging plate kind of thing that allows it to drip down onto the roots. And if you see these things, you'll recognize them because they tend to have a cloud of mist around them. That's why they call them drip mist. But they look basically like this kind of, and then we got this going right here, and then the water comes up through here, and it sprays out under high pressure. It hits the top here and then drips down. There's your drip part, and of course when it hits this area up here, it splashes and sprays out, and you get that mist that's around them. So the mist is also helpful in that the leaves can absorb the mist somewhat, but the main thing is getting that water down to the roots, and this is where it drips down there. So it's a low volume, but it's not a super high pressure washing the soil away as well. So that's the beauty of a drip and mist type system. Then you have contour plowing, is when you farm following the contour of the land. That's correct. So we're not kind of redundant here. We'll call it the shape of the land. Same thing. And what happens is when you have it's used when you have hilly areas for your land, and when you have water that's running at a direct 90-degree angle to your crop rows and things, and you have a dip in the land there, it will tend to wash that out from underneath, erode it underneath. I'll show you a diagram to further illustrate that. But contour plowing reduces that by not plowing in straight lines. When you see a picture of it, you'll see what I mean. They go in curves and everything based upon the shape of the land. Okay. Terracing, we've looked at this before. We saw a picture of this before we talked about water conservation. Water and soil conservation go hand in hand, because it's excess water that will carry that soil away with water erosion. So same thing with your terracing, it slows the water down so it can settle in and doesn't wash all the soil away from the side of that mountain or hill. Strip farming is when you use certain crops like wheat and other grains. That the wheat and grains are grasses, and so they have that root structure, like I said in the last slide, that spreads out and holds the soil in place real well, and therefore that holds it well. But you might not want to grow wheat. There might be a lot of people that are growing wheat, or it might not be that profitable because of that. You can still plant rows of it and then plant something else. Corn, technically, it's a little of both, technically, with corn. I'm going to go ahead and let you have that point because you guys don't really know. But a better example of this would be perhaps peas, in that these are individual plants. So we're looking at individual plant type ones with a more localized root structure. You know, you can pull the plant out of the ground. It doesn't pull all the rest of the plants out of the ground. Whereas with grasses and wheat and those kind of things, they're connected together. They hold the soil in place better. So you can alternate these with those, and that'll help to protect those individual plants. No plow. I'm going to take that because that's another term, typical term that we use for what they call tilling. You know what it means to till the soil? What is that? What do they do when they till the soil? They turn it under. Plowing sometimes is just flattening it out. This is where you actually turn the soil, you're breaking it up. You're exposing it. Lots of nice fresh soil. It's very good for plants to grow in and to sprout and grow very quickly. That's why they do it in farming. However, if you have wind or rainstorm after you've just plowed it, and even worse, after you've put the seed down but it hasn't had time to take root, you can wash and blow all that stuff away very easily. Very subjected to wind and water erosion when it's freshly tilled. Nature doesn't do that. When plants die in nature and the seeds fall on the ground, there's not something that comes and digs up the soil and prepares it for it. So having the plants still in the ground to do that will then hold it in place. A lot of times they'll kill the old crop and then just poke the seeds down through the dead plants that are still there. Or if it's an annual crop, they'll leave the old crop in place rather than tilling the soil and just push. What they have to do is they have to push the seeds down through that level to do so. In construction, believe it or not, you need to conserve soil there. Call it fill dirt. As a matter of fact, we had to pay $2,000 when we made our house. When we built our house for dirt to build up the grade for it, and it was not dirt cheap, as you can tell. And if you've ever seen like that black cloth kind of wall that's around the perimeter of a construction site, that's made to hold that dirt and everything in place. This is for conserving the soil. It's also to reduce water pollution as well. So that's what that's typically for. So those are some of the ways in which you can reduce water erosion. A lot of it has to do with slowing that water down. And then you have wind erosion. That it's not as easy to control because we don't have, we don't determine how much water goes or wind hits it and everything like that. But one of the things you can do is you can plant or maintain trees. Trees act as a wall to the wind and reduce wind erosion that way. That's the way they do it in nature. That's the way, if you preserve a wall of trees on one side of your property, particularly where the prevailing wind is coming across, you can reduce wind erosion considerably. So that's one thing that you can do. As a matter of fact, in China, they've got a huge project that's doing that there, that they're doing now because it is a big problem in China. And also, no-till farming. Just like with water erosion, no-till farming is going to reduce the amount of wind erosion as well. Okay, demineralization prevention, you want to try to keep the soil with its minerals intact. One of the ways that is accomplished is by planting different crops. We call that polyculture. Diverse will work for there, so I'll give you the point for that. But polyculture. And so that, of course, means a variety. It means diverse, different types of crops and plants. The reason being is that different plants take different minerals from the soil. So one of the things we'll learn is that even though a lot of times you have certain minerals that are always there because they're a common part of biological systems, sometimes there's very specific needs for a particular type of mineral, and therefore a plant that needs that mineral can deplete it very quickly. One example of this is citrus fruit and manganese. Okay, manganese is not something you think of as a common mineral, but it is a necessary component in certain types of proteins. And citrus fruit need it. And where they originated from, in the Andes, it's a pretty common mineral in the soil. When they started to try to grow them, they had to figure out that it needed that particular mineral before the citrus industry was able to be planted in other places besides South America. But that's an example of that one particular crop can remove a trace mineral out of the soil and therefore make it so that crop won't grow well anymore. So you want to plant a variety of different things. And similar to that, you also, if it's either a lot of different plants in one area, or in one area you will plant different things each year. They call that crop rotation. Okay. And one of the strategies that is important to follow, or that helps at least in crop rotation, is if you plant legumes at some point in time. Legumes, primarily they're beans, okay? But one of the properties about legumes that makes them special is that they tend to mutualize, they form a relationship with bacteria, in which the bacteria actually grow in their roots, and these particular bacteria can make nitrogen fertilizer from the nitrogen in the air. Now, as I mentioned before, the nitrogen cycle is very complex. This is one part of it. We're going to talk about that more in detail later. But suffice it to say, in this case, it helps to add nitrogen to the soil, these leguminous-type plants. Rice, I'm afraid, is not a type of legume. There's a number of different ones. As I mentioned, beans are on that particular list. That's why we got soybeans here. Alfalfa is as well. Peanuts are legumes. They're neither a pea nor a nut, but they are legumes. So that helps as well. Organic fertilizer. So if you remember, I talked about how chemical fertilizers, although they're very helpful in modern agriculture, they also are very soluble and they can be washed out of the soil very easily. Organic fertilizer, on the other hand, not only does it decompose slower and therefore release its minerals slower, it also has it can retain water. It's spongy. That kind of humus and everything in the soil, like particularly something like peat moss, retains the water, and therefore that helps to reduce the water from running off and taking the soil with it. Okay. Acid deposition. Oh, group 1. We just did air pollution. Well, okay, I get it. I get that. But that's, if you remember, that's kind of a specific one. You know what? I'm going to go ahead and I'll ask you about this. Group 1. How will nitrogen contribute to acid deposition or acid precipitation? 20 words or less.
20 words or less.
And 5 seconds or less.
It's gonna be absorbed into the clouds and then form an acid-like substance.
Do you remember what the nitrogen type compound is that gets absorbed in the clouds?
NOx.
That is good. Good enough. I will give that to you. Okay. Very good, group 1. All right. So, but that is part of the acid rain, yes. But you may remember that I said that a lot of that, the nitrogen, doesn't really come from the fuel as much as it comes from that combustion. But that's okay. The main thing, the main culprit, the main problem when it comes to acid rain is sulfur. Sulfur is the one that has the most component, and it's the one that is actually more in the fuel, whereas a lot of the nitrogen oxides that are formed are from the high temperature of the nitrogen and the oxygen in the atmosphere reacting with each other. Okay. So, limiting that burning of things that contain sulfur, primarily coal. Okay, coal is the one that's usually the big problem there. Since we're trying to control an acid, what type of chemical will we use to control an acid?
Science.
Base. Add a basic chemical, because it's all about that. And same again, once again, using low pressure irrigation. No, I'm sorry. That's not what we want to see there.
Sure.
Okay. In order for once the soil is acidified, that means the minerals are more soluble. But if you don't have a lot of water, also to wash those minerals out, it's not as much of a problem. So if you can reduce that amount of water, generally in conserving water, you're going to not only conserve the soil physically, but you can conserve the chemicals that are in there as well. Okay? All right, let me count up points.